Okay, so I love the story about Dr. Bristol and the lady tasting tea. So we have this null hypothesis that she's guessing. We collect data, right? The data were the 8 cups of tea that she had to taste test and sort into 2 piles of 4, right? Not piles, but 2 groups of 4. And she got 8 out of 8 correct, which was very unlikely to happen. So when your null hypothesis is very unlikely to happen, then you reject it and say, well, no, she wasn't just randomly guessing. All right. So that's the first key insight into statistics for today. And the second key insight we're going to talk about is the standard normal curve. Okay, and this is a good picture of the bell curve. So you can imagine that there's a histogram in here, and the top of the bars are basically on that blue line. Okay, and this is a bell curve. It's not the standard normal. So let me just show you the standard normal. Sorry. The standard normal is centered at 0. Sorry, I didn't quite get the center selected. And it has a standard deviation of 1. Okay. But not all bell curves are like that. There are other bell curves, and this bell curve, and I want to explain this notation too. When you see the capital N here, it means normal. And in statistics, the word normal just means bell-shaped. Okay? And this is a bell-shaped distribution with an average of 500. Okay, so you see right here in the middle. Let's see if I can do a better. Oh, I'm doing a little better. I got cocky, and then towards the top I said something and I screwed it up. But you can see that the center of that bell is at the average of 500, and the standard deviation is about 100. Okay, so this is between the average and 1 standard deviation above average. So the 1 standard deviation goes there. Now, it is hard to find these standard deviations just looking at the graph. You can see that the curve is down, and if the curve would keep going down, bending downward, you'd see that red line instead of the blue line. So what happens is that this place where the bell stops curving down and starts curving out, that's called an inflection point, and that's where the 1 standard deviation is. Okay, so suppose a test has scores that follow this distribution where the average on the test is 500 and it has a standard deviation of 100. And the question is, well, what proportion of the students score below 400? Okay, so we're going to do the same thing that we did before where we use the stats. We're using a different distribution. We were using binom before, but we're putting this in, right? We're putting this in an average of 500, a standard deviation of 100, okay? And then you can see this part is what we're going to shade in red. The where the scores are less than 400 is what we're going to shade. All right. And you can see that the bell curve is now shaded from 400 down below. And then the question is, well, what proportion of students score below that? Okay, and the answer is it's a proportion of areas. So I'm looking at what percentage of the area under the whole bell curve is represented by the shaded region. And you can look at it and eyeball it and say, I don't know, what, 10%, 15%? I mean, I don't know. But we can run it and you can see that the probability is about 15.87%. Okay? And how are we doing that? Well, we're using the stats norm CDF. Remember again that the stats is referring to the SciPy package. So the SciPy package has this function called norm, dot norm, and there's another piece of it called dot CDF. And so we're able to do these calculations. Okay. And then what's the probability that a randomly selected test will have a score below 400? It's the same exact thing. Why? Because when we say we're going to select a test taker at random, well, all the test takers are represented in the bell somewhere. And the ones who scored more highly, of course, are going to be, sorry, you know, we have some people who scored higher, and we have some people who scored in the middle, right? So what percentage, or what's the probability of drawing one score at random? Okay, so we're just going to pick one. Okay, and it can come from anywhere underneath the bell. What's the probability that it happens to land in that shaded region? And the answer is exactly this, 15.87. Why? It's really just the exact same question. So now they're asking the question, what's the chance that you pick a randomly chosen score and it lands between 4 and 700? Okay. So again, we can apply this norm, the stats.norm PDF. And again, the distribution is still has an average of 500 and a standard deviation of 100. And notice now we're telling it to fill between X and Y, where, and this is doing the math to get everything working right, to get between 4 and 700. Okay, and then what happens? Well, we get this nice picture, and it shows us, and that it's what? I don't know. It's maybe 70% of the area under the curve. I don't know. But now they're coming down, we're using a slightly different function. Notice that now we're using the stats.norm.cdf minus the stats.norm.cdf. So we're evaluating the 700 in the first one, the area, the number of people that scored below 700, and then counting up the number of people that scored below 400, and we're subtracting the two. So we're getting rid of this area over here. That's what the subtraction is for. The first thing calculates everything to the left of 700, and the second one calculates the probability of everything to the left of 400, but then we subtract to get rid of this area on the left. Let me erase that so it's not so busy. And you can see that the probability, I guess 70%, it's 81.8, right? So almost 82% chance that you score, that you take this test and score between the 400 and the 700. So this is using statistics to calculate these probabilities. We assume that it's a normal, a bell-shaped distribution with a certain average and a certain standard deviation, and then we can do these calculations with the SciPy functions, the stats norm PMF, the stats norm CDF functions. Don't worry about them. It's good to know them, but you will not be expected to do a lot of programming with them. The dot sample you will use a lot. Okay, so standard units, and this is an important idea, this z-score. So this is a formula. So the z-score for some data point x, its z-score is equal to, you take x minus mu. Now, we have to talk about this, right? Because in statistics, we have average and standard deviation. Those are two of the most important statistics that we have. And we also have this idea of a population, right, and a sample. I'm sorry, this is going to become ugly. See if I can just abbreviate there. SAMP. That sort of looks like SAMP. Okay, so the average in the population is mu, and the standard deviation is sigma. Now these are lowercase mu and lowercase sigma. If you're used to seeing these on, you know, some of the Greek fraternity and sorority letters that they wear on sweatshirts and ball caps, those don't look like the ones you'll see. Why? Because they use the uppercase ones for the Greek fraternities and sororities. These are lowercase. So this is mu, which is a lowercase m, and sigma, which is a lowercase s. And for the sample average, weirdly, we use x bar. X bar is the mean, and s So yeah, you feel like we should maybe use the mean, but remember M could mean median. So X bar is a much more specific way to say the mean of the sample. Okay, so, and you know the difference between the population and the sample, right? If there are, it's a little small number. The number is too small, but just suppose there were 5,000 undergraduates on the Dahlonega campus of UNG. And we were doing a study and we talked to, say, 100 of them. Well, the 5,000 total students at UNG, that's the population. The sample is the number of people that are actually in our study, the ones that actually do our survey or do the experiment in our research. So the sample is just a part of the population. All right, and so the z-score is equal to the data point that we're calculating the z-score for minus the population average divided by the standard deviation from the population. However, a lot of times we don't know these things that I just circled, and so we often are estimating mu, right? We're estimating that using the sample average. And we're estimating the standard deviation using the sample standard deviation. Okay, why do we care about z-scores? Well, so consider this example. We have fraternal twins, Richard and Rachel, and they're both unusually tall. Richard is 6'5", which is pretty tall for a male, and Rachel, who is biological female, is 6'1". Okay, so we can calculate the z-score for both of them. And we'll see, what does the z-score tell us? Well, the z-score tells us how far away from the middle of the bell we are. If you're below average, it's going to be negative and you'll be to the left of center. And if you're taller than average, you will be to the right. So let's take a look. And you see the calculations, right? So what are they doing? This is Rachel's height of 6'1", which is 73 inches, minus the population average. How do we know that? We've gotten that given to us. Remember, the capital N means normal or bell-shaped, and 64 inches is the average, and 4 inches is the standard deviation. Okay, so it's 73 minus 64 divided by 4, which is calculated for us right here. So Rachel's z-score is 2.25. Why is that important? Well, we're going to compare z-scores between Richard and Rachel to see who got the higher z-score, who's farther away from the average height. Okay, and then again, for Richard, we do the same thing. We take the data point minus the population average. Again, that's given to us right here. This is for the males, biological males. 69,3, so that's why we're taking 77 minus 69 divided by 3, and that is approximately equal to, you can see the code, I'm sorry. Well, there isn't code down there, so I'm going to change this code. I'm going to change it to evaluate to what we needed, 77 minus 69 divided by 3. And it turns out, sorry, I can't get this back exactly where I want it. So it turns out that Richard's z-score is about 2.67. And just notice that Richard's z-score is bigger. So he's further away in the bell curve of male heights. He's further away from the center of the male heights distribution than Rachel is from the female heights. Why? Because he had the larger z-score. Okay, sorry about that. You saw my Teams messaging popping up and somebody was asking for help, which is good. I'll be able to go help them in just a second. So let's get here. So what are they doing here? They're showing the, and once again, I'm getting the pop up. Okay, So what is this showing? Well, this is showing that Rachel's height, which is a vertical line here in the bell. So this is how tall Rachel is. And she's well away from the average, right? So she's to the right of the average. And this little percentage is the probability, that area is the probability that you're as tall as Rachel or taller. Okay. Sorry. And if I go down, we're going to do one for Richard, right? And notice that there's just this tiny little, that's how we know that he's further away from the mean. Why? Because there's a much smaller shaded red area in Richard's graph. So the point is that compared to their biological sex, Richard is taller than Rachel is compared, um, if again, you're comparing them to their biological sex. So the empirical rule. All right. And the empirical rule works with any bell-shaped distribution. Sorry, let me just bump up here. And this is important. 68% of any normal population will fall within one standard deviation of the mean. Okay. And within two standard deviations of the mean, we're going to get 95% of all that normal population falling in there. And within three standard deviations of the mean, we get 99.7. Okay, and notice that this will work not just for the standard normal, but for any normal population. There's where it says any normal population will have this property. And before we had computers and it was real easy to calculate this exactly, statisticians did this in their head using the empirical rule. And so what are we going to display here? Oops, sorry. This is within one standard deviation of the mean, and you can see it's shaded. Between -1 is -1 standard deviations away from the mean, or 1 standard deviation below the mean, and the +1 is 1 standard deviation above, and we capture exactly 68%. Sorry, you can't see because my my cursor is in red, so if I change it to blue, maybe you can see if I were to circle the 68%. Okay. And then this is for two standard deviations. Again, it's just a calculation, and we're just having the computer estimate this within two standard deviations of the mean. And there you go. It calculates that 95% of the scores fall within two standard deviations of the mean. And here's the one for within three standard deviations of the mean for 99.7. So that's the empirical rule. Okay, and like I said, we used to do this all the time, these examples. So if you're told that a sample of data is approximately normal with a mean of 50 and a standard deviation of 6, then you know that most of that data, okay, so they're doing 3 times 6. Why? Well, the standard deviation is 6, and they're doing 3 standard deviations. So 50 minus 18 is 32. And 50 plus the 18 is 68. So we know that almost all of the data is between the 32 and the 68, or 99.7%, right, which is calculated out precisely right here. So the empirical rule is really useful. And this is going to be another visualization. Okay, so in the first graph in the top middle, you see that 68% are within one standard deviation of the mean, and the bottom. So this is just another visualization with all the graphics on the same page. So that's all we're going to have for the empirical rule, and we'll move on to the use of probability in statistics, which is the final thing in the notebook. So listen carefully. A statistical test has a preset value called the level of significance, and we usually denote it alpha. So this is the Greek letter alpha, and it's lowercase alpha. And the final output of most hypothesis tests is a p-value, which will be denoted p. And as long as p is less than alpha, we reject the null and say the result is significant. Okay, so let's say that Ron Fisher set alpha at 5%. He said, all right, if there's a less than 5% chance that Muriel can guess, you know, that there's less than a 5% chance that she was guessing at random, we're going to reject that idea. Okay, well, that's what we do in statistics. We have a null hypothesis, and the p-value tells us how likely it is. And if it's unlikely, if it's less than alpha, we're going to reject the null, like Ron Fisher did. He rejected his null hypothesis that Muriel was guessing at random. And the alternative was that no, she was telling the truth. She could actually taste the difference in the tea. Okay, so what is the key about probability and statistics? Well, we're always going to have this p-value that pops out of the statistical test that tells us the probability that our null hypothesis was true. And when p is less than alpha, we're going to find significance. Okay? And we'll talk a lot more about that in the coming weeks. But just remember, if nothing else makes sense out of today, make sure that you get that. If p is less than alpha, then we reject the null and the result is significant. Just like it happened with Ron Fisher and Muriel Bristol, Dr. Muriel Bristol, the lady tasting tea.